Here we have some practice for nomenclature of ethers and thiols. Our first one is an example of a very simple ether where we have two easily named R groups. And in those cases, and only in those cases, we can just name the two R groups and we can put them in alphabetical order. So cyclohexyl, isopropyl, ether. Alternatively, we can name the ring, the cyclohexane, as our parent name. Since there's only a single substituent, we don't need a number, and we can call the substituent, the isopropyl group with the oxygen would become isopropoxy cyclohexane. Either name works though. Question 2, we definitely have a very simple group on the right, just a methyl group, but on the left, definitely a more complicated group. So the ether here just becomes a substituent, and we treat this compound as if we were naming any other alkene. So we're going to number this left to right because the numbering is controlled by the alkenes, not the ether. Again, the ether is just a substituent here. So we have an 8-carbon chain. So this is going to be octane. There's 3 alkenes. Those 3 alkenes are at carbons 1, 3, and 5. So we put those in the name, 1, 3, 5. And because there's 3 alkenes, we call this triene. The ether group, which as we said is just a substituent here, is on the 8th carbon. It's a single carbon methyl, plus the oxygen makes it methoxy. And then finally, yes, we're into second semester organic. Yes, we've got more complicated and more functional groups to name, but still, and we're going to see this throughout the rest of these in this exercise, you can't forget your stereochemistry, whether it's chiral centers with R and S, or whether it's the easy isomers of the alkenes. In this case, 2 out of our 3 alkenes we have to determine E and Z for. The one at this end of the chain, on the left side, has a pair of hydrogens, so E and Z doesn't apply there. But both carbons 3 and 5, those alkenes, we can see that they're trans. But if we're doing them in terms of E and Z, that's going to make them both E. So 3E, 5E. All right, moving on to number 3. Again, more complicated structures here. So our ether groups are just going to be substituents. That means our our numbering is going to be decided based on the functional group that's present, this alkyne. And so we can number it straight across. So this is hexane for 6 carbons. Because it has an alkyne, becomes hexine. And it's going to be hex 1-ine because the alkyne starts on carbon 1. Next, we have the 2 substituents at 4 and 5. Both of these are ethyl groups plus an oxygen, so that makes them ethoxy. So 4,5 diethoxy. Our final step is to determine stereochemistry. And we have two chiral centers in this compound, carbons 4 and 5. And we can see in each case, so for carbon 4, the oxygen has higher priority. The carbon to the right has an oxygen on it, whereas the carbon to the left only has other carbons. So it's going to be 2 here, 3 here. Our lowest priority group, the hydrogen, is already pointing back. So we have R. And then at carbon 4, again, the oxygen is highest priority. The carbon with the oxygen on it is second. And the methyl is third. Lowest priority already points back. Again, clockwise. That makes both of these centers R. And so our stereochemistry, 4R, 5R. All right, our next structure may be a little bit more complicated. Again, these various ether groups are just going to be substituents. So where we number this is going to be based on the alkenes again. And that means we can start either here and go to the right, because that'll give us 1 and 3 for our alkenes, or start there and go counterclockwise. If we start up at the top, we'll get our first substituent on carbon 2. If we start down at the bottom, though, we get our first substituent on carbon 1. So given that both of those directions give us the same numbering for the alkenes, that means we'll go in this direction. So our parent name, cyclohexa 1,3-diene. And then our substituents, carbon 6 has a bromine. Carbon 6 also has a chlorine. The first and third carbons both have ethoxy groups, so diethoxy. And we've run out of room, so we're just going to continue up, and then we'd come back to the cyclohexadiene. And then carbon 5 has a methoxy group. Final thing would be to determine the stereochemistry. This compound has 2 stereocenters. Both carbons 5 and 6 are chiral. Carbon 5, we have an oxygen. That's going to get higher priority than either of the carbons. And then the carbon below is going to be second priority because it's attached to the halogens, whereas this carbon is just attached to other carbons. Lowest priority group, which is the hydrogen, is already pointing back. And so our arrow here at 5 goes counterclockwise for 5s. What about carbon 6? So carbon 6, based on atomic number, bromine is first, chlorine is second, and then both of our carbons have oxygens attached to them. The difference is the carbon here that I've labeled 3 is double bonded to another carbon, whereas our lowest priority carbon up at the top is single bonded to a carbon and also has a hydrogen. So that's going to make the one I've labeled as 3 the third highest priority, and the one at the top is fourth. Now, in order to determine this stereochemistry, you're going to have to rotate this molecule, and you're going to need to rotate it so that you're basically looking at it from this angle. And if you do that, then that'll put your lowest priority group pointed back. And when you do that, you'll see that your arrow going from 1 to 2 to 3 goes counterclockwise, and so we also have 6S. Question 5, we've got our first example of a thiol. Not much else going on in this compound, so that thiol is going to determine the direction that we number this in. So we have a 7 carbon molecule, so the parent name will be heptane. Thiols have probably the easiest name once you're adding them into the parent. Just call them thiol. And the 2, of course, indicates that that thiol is on the second carbon. In addition to that, we do have another substituent. We have this methyl group at carbon 6. So this is 6-methyl. And then what about stereocenters? Carbon 6 is not chiral. It has 2 identical substituents on it, the 2 methyl groups. However, carbon 2 is chiral, and we can see our priorities here, 1, 2, and 3. Arrow is clockwise, and so this is R. Note that in this case, we don't need to put a number in front of the R because it's the only chiral center within the compound. And finally, one last example. Here we have alcohols, we have an ether, and we have a thiol. The highest priority functional group here are the alcohols, so that's going to control how we number it. So we're going to number this one left to right. So 7 carbon molecule makes this heptane. 3 different alcohols. So 2, 3, 4, because that's where those alcohols are. And then because there are 3 of them, triol. We then have 2 substituents. We have the ether here at 5. So that's 5-methoxy because it's a single carbon. And we have the thiol as a substituent. That thiol, when we make it a substituent, doesn't go by the name thiol anymore. We use the term mercapto. So this is 6 mercapto. 5-methoxy. And then, as we've said repeatedly, especially during this video, don't forget your stereocenters, because where are the chiral centers in this compound? Well, honestly, they're almost everywhere. Now, fortunately, these are all relatively straightforward. We have 3 cases, 2, 4, and 5, where the lowest priority group is pointing forward. So you'll do your R and S assignment and then reverse it. And then the other 2 carbons, 3 and 6, that are chiral, have the lowest priority group, a hydrogen pointing away. So you'll assign your R and S and then keep it as is. By the end of that, you should come up with the following: 2R, 3R, 4R, 5S, and 6R. Again, important to remember, even though we're way past the point in this course where we learn stereochemistry, we still need to do the stereochemistry for any compound that we are naming.